Hello, my name is Ben Hicks, and today I'm going to be talking about the triboelectric effect. So first things first, what is the triboelectric effect? Well, the definition of it, the triboelectric effect, is that it is contact electrification in which an object possesses an electrical charge after being separated from the object with which it was in contact. So more simplified, basically what it's saying is when you take two objects and you rub them together, you will have a transference of electrons from one of the objects to the other object. So this means that one object will end up more negatively charged because it will have accumulated more electrons, whereas another object, or the other object in this case that was rubbing against it, will be more positively charged because it will have had its electrons stripped from it. And so this then is the separation of charge that we determine to be the triboelectric effect. An interesting thing to note is that most static electricity is considered to be due to the triboelectric effect. Now, there are other causes of static electricity that aren't necessarily due to the triboelectric effect, but they are going to be not as easily observed in day-to-day life. Two of them are pressure-induced and heat-induced, which the circumstances and conditions for that have to be a little bit more extreme than we're going to see in day-to-day. And then the other one is charge-induced static electricity, and that's going to be more on the atomic level, which is also very difficult to see. So for the most part, that which we will observe in the real world is going to be due to the triboelectric effect. So here is just an image that is going to support and reinforce the definition from the previous slide. So here we have two separate objects that have their charges on them, obviously evenly spaced out. And then we begin to rub these objects together, and following rubbing them together, there has now occurred a separation of the charge. And so in this case, the top object has now accumulated more negative charge, and the bottom object has accumulated more positive charge. Now, something you might be asking yourself is, okay, how do we know where the negative charge goes and where the positive charge goes when these two objects come into contact? Well, that's why we have the triboelectric series. The triboelectric series is just kind of scalar here, and it shows you what objects are going to be more likely to end up with positive and or negative charge when they're rubbed together. And so obviously with this scale too, you would get the best results if you wanted to experiment with the triboelectric effect by using two items from opposite ends of the spectrum. So, air or human body with Teflon or silicone. Obviously air might be a little bit difficult if you wanted to experiment with this because you can't grab air. But if you were to rub the human body, for example, against some Teflon, you would be able to strip a lot of electrons from the human body, thus making the body more positively charged and the Teflon more negatively charged. And so then you can use this in different examples or scenarios to determine kind of where the charges go and why the interaction is occurring that's occurring. So we're going to use that actually and go through a couple of examples of the triboelectric effect, and then I will have kind of a practice problem for you to work on here in a little bit. So first, we have this image of this cat, and it is attached to it has styrofoam peanuts attached to its fur. And so this is due to the triboelectric effect. If we jump back a couple slides here to the triboelectric series, more than likely the cat's fur is going to fall somewhere on this scale between like the wool and the human body. I'd say a cat's fur is probably a little closer to wool, but it's wool, kind of hair, fur. Anyways, it's going to be kind of in the middle of this. So obviously it's going to be more likely to have positive charge, or rather to have negative charges or electrons taken from it. Whereas the styrofoam peanuts from the image are going to be more down towards the celluloid or the urethane or polyethylene kind of range, something, kind of plastic-based materials. So it is going to take electrons and become more negatively charged. So when we go back to this image, obviously what happened here is styrofoam peanuts, as they rubbed against the cat's fur, they removed electrons from the cat's fur. This made the styrofoam peanuts more negatively charged. Then the cat's fur, which then lost these electrons, became more positively charged. And then this positive and negative charge, because opposite charges attract, the negative charge from the styrofoam peanut and the positive charge from the cat's fur caused an attraction and caused the styrofoam peanuts to stick to the cat's fur and the cat's fur to stick to the styrofoam peanuts. And so now this poor cat is covered in styrofoam peanuts. So this is another example, one that I'm sure we've all experienced. You're walking around your house and you go to touch a doorknob and boom, you get zapped. So this can occur for a couple of different reasons. It all kind of depends on what you're wearing on your feet. If you're wearing shoes, the rubber might mean that you are taking electrons, or if you're wearing socks, it means you are losing electrons, more than likely. But as your feet rub against the carpet, and as you either take or lose these electrons, you are going to have a buildup of charge in your body. And then when you go to reach for the doorknob, depending on what this charge buildup is, there will be a leaping of the electrons from the more negative object to the more positive object. So if you've, for example, been walking around in your socks, you are likely going to, we'll say wool socks even, just to make things more straightforward. So if you've been walking around in wool socks, more than likely you have had the electrons stripped more from your body, so you become more positively charged. And then when you go to touch this doorknob, that's a good conductor of electricity, or a good conductor of the flow of electrons. When you go to touch it, electrons are going to jump from the doorknob to your finger in order to kind of equilibrate and balance things out. But if it were to be the other way around, if you had a more negative charge built up in your fingers because you were wearing like rubber-soled shoes or something, when you go to touch the doorknob, the electrons are going to jump from your finger to the doorknob. Okay, so now I have a practice problem for you here. I've made sure to include the Triboelectric series just so that you can use that kind of as a helper as you go through this problem. But I want you to look at this picture here and try to figure out, okay, so why is it that this hair from this child is sticking to the balloon? So I'll give you a few seconds to do that. Go ahead and pause the video, and I'll stop talking for a few seconds, and then go ahead and unpause the video, and we'll go through this together. Okay, so I'm going to assume that you already went through the practice problem, and hopefully you were able to kind of work it out. Essentially what's going on here, so in this case the child's hair, we can equate it essentially to the human body, since it's attached to the child. Since the hair is attached to the child, it's all kind of the same object for the purposes of this thought experiment here. And then the balloon, it's going to fall somewhere on this natural rubber, maybe to polyester range, so it's going to have a pretty good ability to take electrons. So as you take the balloon and you rub it on the head, the balloon is going to strip electrons from the hair. These electrons will then build up on the balloon, and the hair, which has now lost these electrons, becomes positively charged. But because now there's a negative charge on the balloon and a positive charge on the hair, there's an attraction that now exists between them, and so the hair is going to stand up and even stick to the balloon in some cases. And this is, again, all due to the Triboelectric effect. Finally, I just wanted to show one more example, one that I thought is pretty interesting, one that we observe, and that's a pretty brilliant and impressive demonstration of the Triboelectric effect. So what happens is, as water and ice particles begin to interact with each other within kind of these moving turbulent clouds with winds and all of the stuff that's going on in the upper atmosphere, they will begin to kind of strip electrons from each other. And so what happens is a positive charge begins to collect in the top of the clouds, and a negative charge will kind of collect more here at the bottom of the clouds. So then as this negative charge builds up here on the bottom of the clouds, down on the ground, more positive charge is going to be attracted, kind of higher up on the ground, just because there will be so much negative charge that it's going to pull positive charge a little bit closer to it. And so then we'll kind of even get a separation on the ground level of more positive charge being at kind of the upper part of the ground and a more negative charge down on the lower part of the ground. And then eventually there's a certain threshold in which the charges in the sky on the and in the ground connect, and there's this giant electric shock that results in a lightning bolt that strikes the ground and is super powerful and very impressive. So that is everything on the triboelectric effect. I hope you've been able to learn and understand a little bit more about what the triboelectric effect is and how it works. Here is just my reference page, and thank you for watching this video.